Hello. Today, I want to talk about using Taylor series. And I'm going to give you a couple of different applications where you might use Taylor series. The first one, it's possible that you don't have to use Taylor series for it. So you can use other methods that we've used to sort of figure out these things as well. Taylor series just gives you another tool for your toolbox to sort of get this to work. There is one example in there that needs a Taylor series, or would be nice with the Taylor series to do, and then you don't have to go through the derivatives of something nasty. So there's sort of some sort of benefits to using Taylor series, and also some downfalls to using Taylor series as well. Then I want to talk about how to find a function, given a Taylor series. Can you actually figure out what function it is that is represented by that Taylor series? And for that, there's a file in my math lab with a common power series. It's actually from the book, straight from the book. It's just a table of functions with their power series and where they converge, and sort of a very nice, concise place to find these Taylor series. Then finally, I want to talk about the last situation where you probably will use the Taylor series. It's integration. And so if you have a function that you cannot integrate, but it has a nice Taylor series, you can integrate the Taylor series and estimate the integral from your Taylor polynomial rather than your Taylor series. So you're going to use your Taylor series to sort of do the integral, and then you take a Taylor polynomial of that integration, and then you can figure out sort of what is it that you're actually looking at. All right. Let's talk first about limits. So for limits, if you have a limit and you can sort of spot the right thing, you can do this using a Taylor series. So you'll notice the top of this function, this fraction here, goes to 0 as x goes to 0. And the bottom also goes to 0 as x goes to 0. And so you can do this using L'Hopital's rules. You differentiate the top, you differentiate the bottom. What happens when you do that is you get, again, a 0 over 0. So you do the derivative again, and that will give you the limit of this thing. Okay. Now we can skip all of that if we know the Taylor series expansion of e to the x. And so I'm going to actually go to that table for us, just to sort of get you associated with it, you to see it. The Taylor series expansion of e to the x is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the k over k factorial, and so on, right? So you're sort of the sum of these things, x to the k over k factorial for absolute value of x less than 0, less than infinity. So it actually works for all x values you can plug in. So this will always converge no matter what x values you plug in to here. So now if I take the limit of this thing, so I'm going to rewrite the e to the x in my limit using the Taylor series expansion of e to the x. So e to the x was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. And then I have minus x minus 1. And so what I have here, this first thing is the Taylor series expansion of e to the x. It's sort of an infinite polynomial. And then I'm subtracting the x term and the 1 term off of that. And then I'm getting what I need. And then still over 4x squared. And so what we do here is we say, oh, okay, look, the 1 subtracts with the 1, the x subtracts with the x. I'm left with x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, and so on. So I'm going to do this. I'm going to say, oh, well, that's the same as limit as x goes to 0 of just x squared over 2 factorial plus x cubed over 3 factorial plus so on times 1 over 4x squared. And the reason I'm doing this is sort of like the bottom is just going to come up as a 1 over that, and then I multiply. Any term that has an x in it at the end of all of this, which is every term beyond that first one, will go to 0 as x goes to 0. So what I end up with here is just 1 over 8. Okay, now this is the same as doing L'Hopital's rule twice. So I do L'Hopital's rule twice, I get the exact same thing. So it's sort of a question of time saving. So do you remember your Taylor series? If you remember them well enough, possibly this is going to save you some time. If you don't, it probably doesn't save you much time. So the derivative of the top is just e to the x minus 1. and the derivative of the bottom is just 8x. And now the bottom and the top still go to 0. And so the limit x goes to 0 is just going to end up being e to the x on the top. The derivative of the top is just e to the x. Derivative of the bottom is just 8. As x goes to 0, that goes to 1 over 8. I get the same thing. And so there's a question of, so maybe there's not a lot of time saving, but I would like you to try this with the power series in expansion in here. And we'll see another one where it actually is maybe better. It's a good time saver to actually do the Taylor series expansion of this. Okay, so let me give you one more just to sort of show you what exactly we're doing here. I've got t squared 2 cosine t minus 2 over t to the 4th. We go back and we say, oh yeah, cosine has that nice power series expansion. It's the alternating series with 1 minus all the even terms plus all the even terms minus, so all the even terms only, and it's alternating in sign. And so I say, okay, so that's pretty good. So what am I going to get when I plug that back into my expression here? So I'm going to get limit t goes to 0 of t squared, and I'm going to move the 2 over here as well, plus now 2 times the expansion of cosine of t. So that was 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial minus t to the 6th over 6 factorial, and so on, divided by t to the 4th. And so I can kind of go in here and I say, all right, so this means we have the limit as t goes to 0, t squared. Now let's multiply this 2 through. So I get t squared minus 2 plus 2 minus t squared, because 2 is 2 factorial, plus 2t to the 4th over 4 factorial minus 2t to the 6th over 6 factorial, and so on, all divided by t to the 4th. So now I can sort of cancel what I need to. T squareds cancel, negative 2, positive 2 cancel. I'm left with 2t to the 4th over 4 factorial minus 2t to the 6th over 6 factorial plus, and so on. And then I have that multiplied by 1 over t to the 4th, just to make my life a little easier. And then the limit is still as t goes to 0. So what you can see here is that the t to the 4th cancels this t to the 4th. It cancels 2 of these, but leaves 2 of them. And then it leaves t's in every other term beyond that t to the 6th. And so there's sort of every one of those as t goes to 0 will go to 0. And I'm left with just 2 over 4 factorial. And if I could do that, you know, it's just 2 over 24, or 4 times 3 times 2, the 2's cancel. I get 4 times 3, 1 over 12 is what I'm looking at there. So I get 1/12. So here we do save maybe a little bit of time. So if I look at this thing and I say, how many times will I have to apply L'Hopital's rule to this to make it work out? Well, the denominator is not going to go away until I've applied L'Hopital's rule 4 times. So differentiating it 4 times would give me a constant in the denominator, which would be actually 4 factorial. And the numerator, when I differentiate 4 times, I'm going to sort of get this cosine to go to negative sign, then it goes to negative cosine, then it goes to positive sign, then it goes back to cosine. And so 4 times there is going to give me back to cosine. In the middle of all of that, I'm going to end up getting zeros when I do this sort of derivatives. And so I'm going to get zeros throughout. All right. And so I can do that. It's fine to do it 4 times derivatives, but it might save time to sort of look at this power series expansion here. Not going to save you a lot of time. Let me give you one where it will. So the one where it actually is going to be saving you a little bit of time is something like sine of ax and tangent inverse of ax. Now the derivative of inverse tangent is 1 over 1 plus ax quantity squared times an a, and this is just not going to be as nice. So doing that derivative once, well, okay, that's fine. You still can use L'Hopital's rule over and over and over again, but now all of a sudden this sort of numerator term is going to be a lot nastier than it was before. So you're going to get the sort of fraction term in the second one of those, and that's maybe not the nicest thing. So I'm going to go back and I'm going to look and I'm going to say, okay, so sine we looked at, sine of ax, just put an a in for all those, and it's going to be ax quantity cubed over 3 factorial, ax quantity to the fifth over 5 factorial, and so on. So that's nice. And then the inverse tangent actually is not too bad either. It looks a lot like the regular sign. The only difference is they're not factorials in the denominator. You just get 3, 5, 7, 9, 11, so on. So it's the odd number at the bottom instead of the factorial. And so they're a little bit different, but not too much different. And the nice thing about this is that in particular, well, those x terms are going to cancel. And then, you can kind of fiddle with the rest of it to make it work out. All right, so I'm going to grab those two things and I'm going to take them back over here. And I'm going to plug them in. So sine of ax is just this term. Inverse tangent of ax is just this term. And so I can sort of see that, in fact, I get, ax minus ax. So those two are going to cancel. Negative ax cubed over 3 factorial is a cubed x cubed over 3 factorial. Plus a cubed x cubed over 3. And so I can sort of maybe find a common denominator there. So I've got a cubed x cubed over 3 factorial plus, and that's negative, and that's plus a cubed x cubed over 3. Well, what's missing is sort of the denominator has 3 times 2 times 1. I'm missing a 2 in the denominator here. So I need to multiply the top and the bottom by 2 to find a common denominator. This gives me 2 a cubed x cubed minus a cubed x cubed over 3 factorial. So this is nice. I actually do get something a little nicer out of that. And then I can do the same for the 5 terms. So that you get a to the 5th, x to the 5th, minus 4 factorial, a to the 5th, x to the 5th over 5 factorial. And I go from there. I can slide this x cubed into the denominator of each of those fractions. And in the first one, the x cubes will cancel, and I will be left with a 2a cubed over 3 factorial b. And then on the, a cubed over 3 factorial b. And then for every other term, I'm going to have something like an x squared, and I'll have an x to the 4th, and so on. And so each term after that first one will end up being having an x in it. So as x goes to 0, what I end up getting here is just a cubed over 3 factorial b, which is just a cubed over 6b. So in the end, all I get is just a cubed over 6b. And you'll notice the mistake I made there when I subtract 2a cubed minus 2ax cubed minus ax cubed, I just get 1ax cubed. So I'm just going to have an a cubed x cubed over 3 factorial b. And so that's going to be what I end up getting. So I get just a cubed over 6b. Now that's going to be possibly a little bit easier than having to do L'Hopital's rule. So if I do L'Hopital's rule a couple times, you'll notice what I get. So the derivative of the top here is just, cosine ax with an a multiplied by it, because it's the derivative of the inside as well. Minus, well, that's actually like a over 1 plus ax quantity squared all over bx, or 3bx squared. So I do derivative of the top, derivative of the bottom, and then I go from there. Now I have to do it again. The top goes to a minus a, which is 0. And the bottom goes to 0 as x. And so I'm going to have to do it again. And notice I'm going to have to do it a couple more times, in fact. What I will end up getting here is each time the numerator is going to still sort of go to 0. When I differentiate this thing, I've got a denominator. It's going to go from there to 0. And so maybe it's not as convenient to do it this way. In fact, it's sort of turning out to be a lot messier, right? So using those power series might be useful, might be reasonable to do. Okay. The other concept that we want to sort of hammer in here is I want you to be able to look at a given power series, look at a table and say, oh, how would I get that given power series with that table? Okay. And so when I do this, one of the things that I will do is I will sort of start by looking at the function and then sort of figuring out what it is that I'm actually trying to grab or get here. So what I have is I have the sum of minus 1 to the k, x to the 2k over 6 to the k. That's the power series. It starts at 0, goes up to infinity. We go from there. So what I do is I'm going to take that, I'm going to grab it and pull it over to this table of power series. And I'm going to say, oh, okay, so it's an alternating one. So since it's an alternating one, maybe it's here, maybe it's here, maybe it's here, possibly it's here, and so on. So I can sort of grab some of these and I can eliminate some of them as well. So it's probably not an e to the x because I have sort of this sum with a difference and so on. And so I don't have any alternating here. So it doesn't seem like it should be the e to the x. So we're going to try it. All right, so I think of it, it's probably going to be alternating, so I'm going to ignore the rest of it. And then I sort of look at this and I say, so how else can I get this? Well, this is a power, so I'm going to rewrite this as x squared over 6 raised to the k power. I'm going to say, okay, so that's possibly what I want from 0 to infinity. So I'm adding from 0 to infinity. And look at that. It's actually kind of nice. So I might have thought, cosine, because it has a 2k in there, but it doesn't have factorial in the bottom. So having, kind of introducing a factorial in there is not going to be possible. So I'm going to go to the second problem. So to the second equation here, I'm going to say, hey, look, this is the same as this with x squared over 6 plugged in to my equation. So what I should get out of this is this should just be 1 over 1 plus x squared over 6. Okay, so now I go back to this problem and I say, hey, you know what this is going to be? This is going to be 1 over 1 plus x squared over 6. And then I can make this a little bit easier, multiply top and bottom by 6. And then I don't have a denominator in the denominator. Makes it a little bit better. But that's the function that this power series describes. Okay. So it takes a little bit of practice and takes a little bit of experience to sort of spot which one of these things am I supposed to have, what am I supposed to take, and then you can go from there. So let me give you another one. So I'm going to have the sum x to the k over k, and k equals 1 to infinity. And I'm going to go back over here and I'm going to look and say, okay, so let's see if we can spot this one. Oh, in fact, look at that. It's exactly this expression. Okay, so what I get here is negative natural log of 1 minus x. And that's exactly the expression I get. I don't have to plug anything in for x because that's the exact expression I'm given. All right. By the way, this expression comes from the integration of that expression. So I integrate 1 over 1 minus x and I get negative natural log of 1 minus x. Integrating each of these terms gives me x squared over 2, x cubed over 3, x to the 4th over 4, and so on. And so that's how I get from one to the other. Okay. And now I go back over here and I say, hey, look at that. I found exactly what it needed to be. So this expression is just negative natural log of 1 minus x. Okay. So the last thing we want to sort of talk about is how do I find integrals using these Taylor series expansions? So one of the problems you might be asked to do is sort of use the Taylor series to estimate the integral within 5 to the 10 times 10 to the negative 4th. All right. And so what you want to do is you want to go through and figure out, using the Taylor series, what the integral is going to be, and then use that series, whatever I get when I integrate the Taylor series, to find an estimate. All right, so I'm going to integrate e to the negative x squared. And the first thing you might do, and the first thing you should do, is you should say, can I do this integration? So can I actually figure out a way to integrate this? So I have some options, right? So I could try integration by parts. My two parts would be maybe e to the negative x squared and 1. So I integrate 1 to get x. I differentiate e to the negative x squared, and oh shoot, I'm going to get like an x squared in my outside term here, and then it's still not going to be in. I can't take that integral, and you can sort of go at this over and over and over again and try to get it, and it's not going to give me something nice. So this I cannot integrate using integration by parts. I have other options to do. None of those options will work. So in particular, this is not going to give me something nice for any of the options that I could possibly want. So I want to use the Taylor series to approximate this integral. So the Taylor series of e to the negative x squared, again, I kind of go back to my common power series and say, oh, I'll put a minus x squared in for each of the x's in this e to the x expression. So I'm going to get 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 6 factorial and so on. And then go from there. All right, so that's my expression here. And then I want to integrate this. So the integral from 0 to 1 of this thing, I want to integrate this thing and then plug in 1 and 0 and subtract the 2 and see what I get. All right. So plugging this in, I get x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial plus x to the 9th over 9 times 4 factorial minus x to the 11th over 11, and it'll be times 5 factorial plus x to the 12th, or x to the, 11th, 13th over 13, 6 factorial, and so on. So I sort of have all of these terms, and then I want to plug in to an expression. So I sort of do this, and I get all the odd powers of x over the odd number, and then I end up with a k factorial on the bottom, and I get minus 1 with k, and so go from there. And so then I know that's my integral, and I plug in 0 and 1. So if I plug in 0, this thing all goes away. Plug in 1, I just get the expression without the x term. So I just ignore the x term. That's going to be the expression when I plug in 1. Subtracting off where I plug in 0 doesn't do anything. So this integral is just going to be exactly this infinite sum. All right. And so now what? So now I just have to look at this thing and say, well, I want to know where is it going to be close as 5 times 10 to the negative 4th to the actual value. So I need to think about the error here. Well, this is an alternating series, and in an alternating series, the error is the absolute value of the next term. And so what I need to do is I sort of need to think, okay, so the error here is going to be the absolute value of negative 1 to the n plus 1 over 2 times n plus 1 times n plus 1 factorial. So it's like 1 over 2n plus 3n n plus 1 factorial. And what I do is then say, okay, so I need that to be within 5 times 10 to the negative 4th. So less than 5 times 10 to the negative 4th. And unfortunately, at this point, we're just going to do it. We're just going to plug in numbers for n and see if I can figure out what n should I choose in order for this to work out. And the answer is actually n equals 5. So at n equals 5, what I get is 13 and 6 factorial. 13 times 6 factorial, 1 over that is approximately 1.07 times 10 to the negative 4th. That's smaller than 5 times 10 to the negative 4th. If I plug in 4, I don't get something smaller than 5 times 10 to the negative 4th. So this is the first point where I cross over that threshold. So 5 is the right value that I need to take. I need to take 5 terms in this sum in order to estimate this integral within 5 times 10 to the negative 4th of the actual value. Okay, so taking 5 terms of this, and sort of, I shouldn't say 5 terms, it's actually 6 terms. It's when n equals 5, you start with 0, so you add extra term in there for that one. I take this alternating sum, I get approximately 0.747, and I don't give any more decimal places after that because I know I'm correct within like 0.0005. So I'm right within then, so the rounding is going to be okay, but I only get 3 decimal places exactly right. So that 0.747 is the exact value of this integral to 3 decimal places. So then I can go from there. So more accuracy, I would just take more terms to get more accuracy. All right. So as a sort of summary here, we can usually use other methods for finding the limit. So usually you can use the L'Hopital's rule. MyMathLab doesn't care what method you use. They tell you, we want you to try to use the Taylor series. All right. So we want you to try, I do want you to try to use the Taylor series for that one. But say on an exam, maybe the L'Hopital's rule is really fast and easy. So you just do L'Hopital's rule, plug in the answer, it's gonna be okay, you know. But if you sort of don't need to do that, you can sort of use the Taylor series expansion to do it. It's also possible you might find, say, a solution to differential equation or some other solution as a power series. and then I need to use those known power series to find the original function. So that's one of the situations you're gonna get into here. You're gonna say, oh, I found this nice power series. What is that as a function? So can I find what function that thing is an expression of? Then I can figure out what the function should be for the solution to some differential equation or some other power series, so other solution to another problem, right? Finally, for the integral, it is actually useful to estimate using the power series. I believe it's actually going to be faster than doing like a Riemann sum. So the Riemann sum stuff, yeah, your computer will do the Riemann sum stuff, and your calculator will do that. Your calculator, it's going to maybe be a little harder to do the power series, but in fact, it's nice to get the exact value using the power series. It's a lot faster for you to do it by hand, especially. So that's a nice thing to do. Plus, you also have some bound on the error with the Riemann sum. Well, I mean, we don't have a whole lot of bound on the error. We just have to sort of work with this. All right. And with that, I think I'm going to end it, and then I will see you next time. Next time, we're going to talk about something very different. We're going to be starting into other ways to express functions in the xy plane other than just a function f of x. So it's not y equals f of x anymore. Now we're going to say, well, there's other ways to do it, and they're going to be useful for these situations. So there's a lot of situations where that will be a useful thing to know. So we'll talk about that next time. All right.